Greetings, welcome to today's lesson on standard form of a linear equation. So far in this series we've looked at slope form and slope-intercept form, which to be truthful are far better forms than the one we're going to look at right now. But this form has one, maybe two really good uses that the other ones don't have. Okay, and that's what we're going to look at today. So we're just going to familiarize ourselves with standard form and then how we can manipulate standard form a little. We're actually going to transform into standard form as well. That's going to be another aspect of what we're going to do here. So let's start with what is standard form. Okay, so standard form looks like this. Here's the generic version. Capital A, X, plus capital B, Y, equals capital C. Now what do the capital A, B, and C stand for? Absolutely nothing. They are not representative of anything. They don't tell us anything about how the graph looks. They don't tell us anything about where the intercepts are or any point that is represented. There's really no information connected to this form. But it's one of those forms that people like because they can utilize it. They can, if I have to make up a linear equation, it's very easy to put it in standard form because it's just got this sort of flow to it. So sometimes people go, okay, how about 2x plus 3y equals 6? Ta-da, look, an equation in standard form. Okay, is that useful to us in any way? Not really. In fact, if I were going to use this, if I wanted to graph it, I would have to change this. I would not use this. The only thing it is good for, I take that back, it has one use, and that was something we saw a while back when we were looking for intercepts. If all I want are the two intercepts, the x-intercept and the y-intercept, standard form is actually pretty good for that because when you put 0 in for x and solve for y, you're almost done. When you put in 0 for y and solve for x, you're almost done. So let's do that. Let's say, hey, what if I, find the intercepts? Okay, remember when you're looking for an intercept, the other value is 0. So if I'm looking for the x-intercept, I make y a 0. Well, if y is 0, that's just 0. So then it's 2x equals 6. I divide by 2, and x equals 3. And that means I have the point 3, 0. If I then want to find the y-intercept, I'm going to replace the x with a 0. So that's going to be a 0 plus 3y. And again, that just means the 0 is gone. So 3y, I'm dividing by 3, and y equals 2. And now I have my two intercepts. So that's the best use for standard form, is it's really the easiest to find the intercepts. Even if the intercepts were ugly. Now these were nice. They were nice whole numbers. But what if instead of a 2x, I had a 5x, and when I divided the 6 by 5, I'd get 6/5, or 1.2. So it's got that advantage. That's one of the most useful times for it. But honestly, the other forms are probably still better than this one for finding the intercepts. This one's okay, but the others are probably even still better. Certainly the slope-intercept form is better because the y-intercept is right there already done. All you got to do is find the x-intercept. So you're halfway done. So that one's still a better format than this one. Okay, but we have a use for it. Okay, we absolutely do. We're going to use it, especially when we get into solving systems of linear equations, which is where we're taking two linear equations and trying to figure out where they intersect. Okay, now one of the things that we might be asked to do with this form, and I'm going to keep these little 2 points right here available to me because I'm going to keep using that equation. What we're often asked to do with this equation is rewrite it in slope-intercept form. We don't like standard form because it's not very descriptive. It doesn't tell us where to plot any points. We can use it to find intercepts, but those still might not be very good. If the intercepts were ugly, then we might be very unhappy with, oh, I don't want to have to graph this because my intercepts are 1.2 and 6.3. Ugh, I don't want to graph that, or heaven forbid it's repeating. I don't want to have to graph that. So what I'd like to do is I'd like to be able to rewrite this equation in a different format. So let's get this into, so we might be asked to rewrite in slope intercept form. This is the always most desirable form we are ever going to be looking at. All forever, really. It doesn't get to be a better linear equation form than slope-intercept form. It's the most descriptive. It's always the easiest to graph because it's nearest to the middle. It's got so much going for it. We can do that. It's not that hard. It's really just 2 steps. And knowing, again, I want this to look like that really helps determine what those 2 steps are. Because I want this, 2x, I want it right there, right? Because I want it right after the equal sign, I want the mx. So that means I want to get rid of it from the left-hand side. And anytime I want to get rid of something, I simply subtract it. If it were negative and you subtract the negative, you'll see yourself adding a positive. But for our purposes here, we're just going to subtract. So this is going to be gone, and I'm going to have 3y equals, and remember how I want it to look. I want mx. Well, that's this right here, negative 2x. Positive 6 plus b. Okay? We're almost there. Looks pretty close, except that this doesn't have a number in front of it. It's always a 1. So that means I need to do one more step, and that is to divide everything by whatever number is next to the y. So the 2 steps are going to be the same every time. To transform from standard form to slope-intercept form, we're going to subtract the x term from both sides. And even though it's not on the right-hand side, so we're going to get a negative, or we're going to get its opposite. Maybe that's even better. We're going to get its opposite. So if this were a negative value of x, I'd get a positive 1 over there. If this is a positive 1, I'm going to get a negative 1 over there, because I'm always going to do this. This is going to be that first step. And then the second step is going to be to divide everything by the number next to y, whatever it is. In this case, 3. So that's going to reduce these 3's down, leave me with just 1y. I'm not going to do a decimal, never decimals. Fractions we like because then they have a rise and a run. It makes it easier to graph. Negative 2 over 3, x. 6 divided by 3 is positive 2. And now I have an equation in slope-intercept form. I know a lot now. I know what the slope looks like. I know that this is a line going down from left to right. I know that it's crossing the y-axis at the number 2. Remember, we found that when we found the intercepts when we started this problem. But now it's really obvious because it's right there in front of me. It's part of the equation. And we are going to be going back the other way at some point. Okay, we are going to take an equation from slope-intercept form and transform it into standard form. So let's take a look at what that would look like. Okay. So take a moment. Remember, 2 steps. It's always going to be those 2. Sometimes only 1, because one of those steps might already be done for whatever reason. Really not. I mean, okay. So that's rewriting it from standard form into slope-intercept form. And you will be asked to write something from slope-intercept form into standard form. So let's just do one. Y equals 2x minus 1. The best part about this is writing from slope-intercept into standard form takes no effort at all. Remember, we want it to be ax plus by equals c. Well, I got the y right next to the equal sign. I need to move the x over. So I'm going to subtract it. Notice where I'm putting it. I'm putting it in the front because that's where I want it. Negative 2x, positive y, and if you had to envision the b value, it would be a 1, equals negative 1. Very easy to go from slope-intercept to standard form. Little more, now this one obviously would only be 1 step to go back because the y value is only 1. If the y value had another value, then... Now sometimes you'll see them, they'll multiply everything, and we're going to talk about that in just a moment, why that would be useful. Okay? And that is if we had some kind of like a fraction for the x, for the slope. Okay? All right, so we've written equations. We've gone from slope-intercept to standard, from standard to slope-intercept. Why do we like standard form? Standard form still seems like kind of a crappy form. Why do we want to do this? So let me show you where standard form has its weird kind of value. Okay, and it leads into this when we get into systems. When we start trying to figure out where two lines intersect, standard form has a value. Okay, but before we can do that, we have to see what's the advantage that we can have. That what does standard form offer us that maybe that slope-intercept form doesn't, or point slope form doesn't. Okay, and that is this. You're going to be asked in various assignments, and this is something that leads up to what we're going to use it for in the future, right? This is like, we're going to ask you to do something, you're going to go, why am I doing that? It'll have a value later. Right now, they're just asking you to do it. They'll ask you to write two equations in standard form equivalent to, and then we're going to give, I'm just going to make a nice easy one. How about 3x plus 4y equals 7? Okay? Now, what do they mean when they say two equations that are equivalent to this equation? Okay? This goes back to, I'd say, probably around the 4th grade when you were asked to write two fractions that were equivalent to 1/2. Okay? So if I said, give me two fractions that are equivalent to 1/2, you'd go, well, if we multiply the top and the bottom by 2, we get 2/4. That's equal to 1/2. I could multiply this one again by 2, and I'd get 4/8. And that's also equivalent to 1/2. Those are all fractions equivalent to 1/2. Okay? All we're doing is changing the way something looks. Remember, we did that in the 4th grade so we could add fractions when they had different denominators. We could use this to create a common denominator. Well, that's exactly what we're going to do here, except that we're not going to create a common denominator. What we're going to create is something called a common coefficient. A coefficient is the number in front of a variable. So the coefficient of x is 3, the coefficient of y is 4. If I had a second equation, remember this is all about when we get to systems, that had different coefficients, and I wanted them to have the same coefficients, this is what I would do. So here we go. I would take my equation, 3x plus 4y equals 7, and I would multiply everything, just like I did a minute ago with the fractions, by 2. Why 2? No reason. I could multiply by 3. In fact, I will. I'll do it again because I want two equations that are equivalent. I could multiply by 10. I can multiply by -5. There's nothing. I could multiply by 3.7218. It doesn't matter. What I'm doing is I'm creating another equation where everything is different looking, but it still represents the same line. So then we do the distributive property all the way. 6x plus 8y equals 14. I have now written another equation that is equivalent to the first equation. Meaning, if I were to make a table of values and go ahead and graph this, these are actually the same line. They wouldn't like, it's not like they're next to each other. They would overlap. They are the same exact line. Okay? Now I want a second equation. What do I multiply by? Whatever I want. Doesn't matter. Does not matter. Just like I did with the fraction, I can multiply this one by 2. Distribute. 12x plus 16y equals 28. And I can do this forever. There's no restriction. There's nothing stopping me from having 40, 50, 60 equations. Okay? This is so I can have a common coefficient when I have 2 or more equations. Just like what I would do if I had 2 fractions and I need a common denominator, I would multiply one or both of the fractions to get that common denominator. Here I'm going to multiply one or both equations to get a common coefficient. It is the same skill that you used in the 4th grade. It just is going to find itself in a very different setting, and that is trying to figure out where two lines intersect. Okay, and that is something that we will deal with when we get to systems of linear equations, which is about 4 lessons from here. Well, actually, that's not even true. It's like 2 lessons from here. But we won't get to utilize this skill in that context for 4 more lessons. But when we do, you're going to look at it and go, oh, now I understand why he was showing us that. And you'll see and you'll say, okay, I get that. Wow, that's a very useful, that works. I like that. That's kind of neat because it's sort of like figuring out where 2 lines intersect without figuring out where they actually intersect, without actually looking for an intersection, just like mathing it out. It's neat. Okay, so we need to be able to write an equation from standard form into slope-intercept, from slope-intercept back into standard form, and then we need to be able to come up with equivalent equations by multiplying, and you just multiply everything, okay? You just multiply everything by whatever number you like, okay? There'll be a reason for why you'll want to do it later, for the same reason like why did you multiply, you know, if you had the fraction 1/2 plus 3/5, right? Well, we're not allowed to add those because they don't have a common denominator. But if I multiply the top by 5/5, and I multiply the bottom by 2/2, now I have a common denominator. So why did I choose 2 and 5? Well, because of the way the problem was written. Because I knew I wanted a common denominator of 10, and that's what was going to let it happen. When you start to do right now we're just doing like change the fraction to whatever, change the equation to whatever. Eventually you'll have a specific thing you want to change it into, and that's when you will apply this process to whatever it is that you're looking for. Okay? So I hope that helps, and I will see you in class.